side?
I think that's just about everyone. I think Joanna and Libby are going to stay upstairs and do field camp.
Yeah, so, okay. Well, so if that's all five of us, and we all know Gray, I'm still gonna do the quick introduction. And so Gray graduated from Emory with a bachelor's in environmental science. He worked for Georgia Department of Transportation for 3 years. And he's one of the fastest master students that I have, and also one of the easiest, put it this way. So it's kind of good. So his presentation is about 30 minutes. He got quite a few stuff to cover. And so I just hand this over to him.
Thanks, Ping. All right, good morning, everyone. I hope everyone is having a great day today. So as Ping said, my name is Gray Vickery, and today I'm going to be sharing some research that I've been working on for about the past 2 years now, where we've been looking at a local estuary here in Tampa Bay known as Fort DeSoto Bay, which is shown on this title slide here. And what we've been looking at is kind of how different factors that have happened at this estuary have affected the circulation patterns here, and what sort of implications that might have, for the water quality here, for the ecosystem connectivity, and for the overall quality of this habitat. So we have quite a lot to cover, so I'm going to go ahead and get started. Okay, so a quick outline for today's presentation. Going to start with an introduction, give a little bit of history on the project, kind of explain sort of the impetus behind this research. I'll move on to, from there to a quick discussion of some very fundamental sort of estuarine processes. And this is actually information that I took directly from my literature review. And then I'll move on from there to a quick discussion of our study area. From there, I'll touch on our objectives and kind of specifically talking about how our objectives sort of shaped our overall research design. And then I'll move on from there to our methods, starting with our field work, moving to our model setup and calibration, and then end with a discussion of our modeling scenarios, like the one you're looking at on this slide here, this neat animation that we made. And then I'll move on to our results. Like Ping said, we do have a lot of information to present. So what I've kind of done is sort of like a highlight-driven approach, sort of extracted some of our preferred modeling cases. But if you do want to see the full results, please refer to the thesis document. And then summary and Q&A session. Okay, so a little bit of background. So the research that I'm going to be presenting here today is actually just a small part of a very much larger research project called the Fort DeSoto Recirculation and Seagrass Recovery Project. Now, the particular portion of this project that we're involved with is actually considered phase 2. So phase 1 actually started back in 2004, and that basically involved the installation of this circulation bridge in the southern portion of the bay, just to connect this, western cell here, western cell with the central cell. And I'll get into this in great detail later. Phase 2, which was initiated back in 2016, is sort of where we come in. So basically what that involved was the construction of a second tidal bridge on this maintenance causeway here. So included in this second phase of the project, there was actually 6 different subtasks. So those included planting native vegetation around the bridges, seagrasses and mangroves. 3 years of seagrass monitoring. You can see an individual here doing a quadrat survey near one of the bridge openings, kind of just to monitor the recovery of those seagrasses in that area. 2 years of benthic sampling, 3 years of water quality monitoring. You can see a scientist with NOAA doing some of that water quality work near one of the bridges. And then, of course, our task number 2, is the creation of the hydrodynamic model. Basically just to quantify the influence of those 2 bridges I showed on this last slide on the overall circulation patterns, specifically in this southern region of the bay. Okay, so before I go too much further, I want to pause for a moment and share some information from my literature review, basically just emphasizing the importance of estuarine circulation, right? So we have to remember that estuaries like Fort DeSoto are tidally influenced systems. So all of the ecological and biological processes that happen within these systems are going to be strongly dependent on that rhythmic, ebbing and flooding of the tides every 6 hours. So as far as water quality is concerned, the pH of the water, the clarity, the dissolved oxygen, temperature, even the nutrient balance, all of these parameters are going to be mediated by that circulation, that rhythmic ebbing and flooding. So when some sort of a barrier, a tidal barrier, is put into the estuary that obstructs that circulation, you start to get areas that stagnate. right? And when you have stagnant water, you get temperature loading. When you have temperature loading, you have reduced dissolved oxygen, and then so on and so forth. Eventually, you have a collapse of the ecosystem. But beyond water quality, there's a number of ecological processes that are also kind of linked and dependent on this tidal circulation. So this image here, this diagram, is actually showing a process called outwelling. So it turns out that a great percentage of the organic material that is derived within the estuary environment is actually exported from the estuary out through these tidal inlets to the marine environments, where those longshore transports will kind of rework it, and then eventually it will deposit on the beach as beach wrack. And it turns out this is a very important process because these intertidal ecosystems actually rely on this energy subsidy. They really need it. They really need this sort of auxiliary energy input. So without that circulation regime, this entire process can shut down. And then seagrass health. So, seagrasses, it turns out when we look at kind of like the environments that are most conducive to seagrass health, we actually see that seagrasses are more efficient at taking up nutrients in a high flow environment than in a low flow environment. So when the estuary itself is better circulated, you have more rapid transfer of nutrients to the leaf surface, which in turn means that you have a more productive seagrass population. So for all of these reasons, right, water quality, ecological processes, seagrasses, the list goes on and on. For all of these reasons, circulation is really seen as a very critical component to restoring estuaries, right? And any sort of strategy that's aimed at restoring an estuary that doesn't specifically address circulation is likely to be ineffective. Okay, so now that we've established that circulation is extremely important, I want to talk about what sort of factors actually influence circulation. So on that last slide, we kind of talked about how the hydrodynamic regime influences seagrasses, but that relationship goes both ways. So those seagrasses actually influence the hydrodynamic regime as well. So the seagrasses exert a very, very powerful frictional force on the flow field that can actually attenuate wave energy and affect the overall circulation patterns. And the degree that these seagrasses are able to do this is usually a function of these 4 parameters right here. So canopy height, shoot density, meadow length, and blade thickness. And when we look at all the different seagrass species that we have in Tampa Bay, there's one that stands out. There's one that kind of consistently scores the highest on these 4 different parameters. And that would be Thalassia testudinum, which is turtle grass. And it turns out that our study area for DeSoto is actually home to the most extensive Thalassia beds in all of Tampa Bay. So needless to say, these seagrasses that we have in our study area play a very major role in the circulation patterns. And this is something that we had to account for in the numerical model that we created to simulate these currents. And later in a few slides, I'll show you exactly how we did that. The next factor influencing circulation, this one should be pretty obvious, causeways. Right? Causeways essentially just act as physical barriers that obstruct the movement of tidal currents from one part of the bay to the other. And you remember from my last slide earlier, when you obstruct tidal circulation, you get issues with water quality. You have stagnant areas, you have reduced dissolved oxygen, and eventually this causes die-offs of seagrasses. It can actually cause a collapse in the ecosystem over time. But of course, there's kind of more to it than that. So these causeways also fragment the habitat. Right? And there's a number of different estuarine organisms that kind of need to disperse to different areas, right? They need to access new resources. They need to complete their life cycle in a different part of the bay. And with these causeways here, it can actually have a very negative impact on those population dynamics. Okay, the last factor I want to talk about, dredge channels. So this diagram here kind of shows the typical geometry of a dredge channel that you might find in Tampa Bay. So it's sort of V-shaped in cross-section, flat on the bottom. What I want you to take away from this is that these dredge channels are deeper than the surrounding areas, and they lack those seagrasses, right? And if you look at this graph here, when the water depth increases, you have a decrease in friction, right? When the vegetation decreases, you also have a decrease in friction. So those 2 factors together make these dredge channels almost behave like these giant tidal conduits, right? That concentrate the flow of tidal currents entering these estuaries. And really, overall, this can have a very significant effect on the hydrodynamics. This is also something that we have in our study area. I'll show you that in a moment. And this is also something that we had to account for in our model. Okay, moving on to the study area. So just to make sure everyone is oriented, Fort DeSoto is located right here at the mouth of Tampa Bay. kind of at the southern tip of St. Petersburg. It's basically this hook-shaped barrier island. We have Egmont Key to the south, and we have Shell Key to the north. Okay, so when we look at some of the aerial photos, kind of comparing Fort DeSoto back in 1943, right, before all of those modifications took place, like 10 years, almost 10 years before those modifications take place. And then we compare that with an aerial photo from today, we can start to see some of those engineering activities that have taken place. The most obvious feature, of course, is this giant causeway that kind of divides the entire bay in half. There's also this second causeway here that leads to this maintenance road. So these causeways have effectively divided the estuary into these three compartments, these three separate compartments. And there was no hydrologic connectivity between them because the causeways were blocking it. So of course, this led to stagnant water, this led to water quality issues, and eventually this led to necrosis of seagrasses and eventually die-offs of seagrasses in the southern portion of the bay. Now these causeways are not the only thing here that are affecting the circulation patterns. If you look closely, you can see this sort of lattice work, this network of dredge channels that is kind of gouged throughout the bay. Now these dredge channels, as I mentioned before, they're a little bit deeper than the surrounding areas, and they're also lacking that vegetation. So as a result, they're going to have greater velocity than other areas of the bay where you might have seagrasses. So one of our goals here was to kind of tease this out and figure out how the dredge channels and the causeways together are influencing the circulation patterns. Okay, so a little bit more on the causeways. So in an effort to ameliorate some of those water quality conditions down in the southern portion of the bay, the county actually decided to install a pair of bridges, right? Install a pair of bridges basically to breach the causeway and restore that west to east connectivity between these three cells of the bay. So that first bridge was built in 2004 on the main entrance causeway, second bridge in 2016 on this maintenance causeway. And I mean, really the overall goal here was just to improve ecological connectivity, improve water quality, and restore seagrasses in this region of the bay. Okay, so clearly we have a lot going on in this estuary, right? We have dredge channels, we have causeways, we have bridges, seagrass beds. And so our overall goal here was to construct a numerical model that would allow us to connect all of this information and evaluate quantitatively how these various features are influencing the overall circulation patterns. Okay, so moving on to fieldwork. We had to collect 3 different data sets to drive our model. The first data set was the bathymetry, right, which you can see me doing some RTK work on the top left here. We used a variety of different devices to collect our bathymetry. One of them was this RTK. But basically, this is just the topography of the seafloor, right? And this is what we use to actually construct the physical domain to run our model. And then the tide level data is actually, you can see us going out to service one of our tide stations down here. The tide level data is used to drive the model, right? This is the driving force for the numerical model, that those sort of fluctuations in water level. And then the current velocity data, which you can see in the top right and bottom left here, that is not used to drive the model in the same way that the tide level data is. Instead, this velocity data is used to kind of verify that our model is working correctly. Because at the end of the day, what it outputs is velocity data. So if we actually have some measured velocity data to compare our modeled velocity data to, then we'll know for sure that our model is working as it's supposed to. Excuse me. Okay, so moving on to calibration. So as I mentioned before, Fort DeSoto is kind of this patchwork of these dredge channels and these seagrass beds. And the frictional characteristics of these two environments differs quite drastically. And this had to be accounted for in the calibration of the numerical model. So to do that, we actually digitized the areas in the bay where we had dredge channels, and we assigned a lower friction value to these areas and a higher friction value to the seagrass beds. And then what we were able to do is sort of gradually turn up and turn down the friction values of these two sub-environments until our modeled values and our measured values were almost identical. And to actually do that comparison, we use this equation here. It's called the Wilmot scale. It looks complicated, but it's actually a pretty straightforward equation. So you just plug in your model values, you plug in your measured values, and then this equation will spit out a value between 0 and 1, right? If you have 1, it means perfect one-to-one agreement between your model data set and your measured data set. A 0 means absolutely no agreement at all. So when we used a friction value of 0.03 for the channels and 0.055 for the seagrass beds, we were actually able to achieve a Wilmot scale of 0.97, which is very high. We were totally satisfied with that. And so we decided to use that friction value for all of our subsequent model runs. Okay, so now the moment everyone has been waiting for, the modeling scenarios. So on the right here, you can see the full list of modeling scenarios that we ran. There were 10 scenarios total. The first 4 of those scenarios we're calling actual scenarios. And we're calling them this because they're based off of conditions that either exist today, right, which is the case for case A2, or have existed at some point in the past, which would be the case for case A3, for example, pre-development. We also ran 6 hypothetical cases. So this is where we got to get a little bit creative. We got to kind of play around with the configurations, to see how different changes to the environment would affect the flow field. So for example, hypothetical case 4, we decided to fill in those 2 north-south oriented dredge channels and kind of see how that would affect the flow patterns. Now for each of these cases, all 10 of these, we extracted velocity data at these 11 different extraction points, as you can see on this map here. And these extraction points were actually positioned strategically in areas in the bay that we expected to see some sort of a response, right? So dredge channels, that would be a great place to place them. Seagrasses, we got some there as well. And then of course, at those 2 bridge openings as well, we wanted to see what sort of a response these changes would have at those locations. So for each of these cases, we basically compared the velocity data at these extraction points for all 10 of these modeling scenarios. And basically that starts to give us a sense of which of these scenarios, gives us the best velocity, the best circulation, and which of these scenarios kind of gives us the most restricted circulation. Okay, so this is the last slide before I get to the results. So one thing that you can do with the model is create these difference maps, where you're basically just comparing 2 different cases to see how the velocity is affected. Right, so for example, in this image here, you're looking at a comparison of the existing conditions, right, case A2, remember from that last slide, case A2, to the natural conditions, which is case A3. So the cooler colors here on this map are basically showing areas where flow has increased, and the warmer colors are showing areas where flow has decreased. So you immediately can tell that there's been an increase in flow in those dredge channels and a decrease in those seagrass beds. So for each of our 10 cases, we created these difference maps that kind of allowed us to tease out these really subtle changes in the circulation patterns. Okay, so now moving on to the results. So as I mentioned before, we do have a very large volume of data. So much data, in fact, that we found that it was kind of difficult to present this all in a systematic sort of way. So what we ended up doing instead was using this highlight-driven approach, where we sort of combed through our data set and we looked for these inflection points, right? These areas where we see drastically high or drastically low velocity values. And then we could kind of focus in on these areas and say, okay, what exactly is going on here? What's causing these differences? What can we learn from this? And ultimately, we really found that this was the best way that we could handle this large volume of data in a way that wasn't completely overwhelming, both to us and the person, the audience that we're actually presenting to. Okay, so moving on to the results. So once our model was calibrated, the first thing we decided to do was something called tidal prism analysis. Now, for those who aren't familiar with the term, tidal prism is essentially just the volume of water that flows into or out of an estuary between high and low tide. Right, so it's just a volume, cubic meters or cubic feet or whatever you want to use. Just a length times a width times a height. You can see this equation here is how we calculated it. But what you can do is you can also calculate the discharge at these 2 bridge openings, right, which you see in this equation here. And when you compare the discharge at these bridge openings with the tidal prism, you can start to get a sense for how these 2 bridges are actually contributing to that overall circulation pattern in the southern portion of the bay here. And when we did this for this lower portion of the bay, we actually found that about 25% of the flood tidal prism during a tidal cycle is actually conveyed through those 2 bridges. So what that tells us, that's a pretty significant finding. And what that tells us is that these 2 bridges are playing a very, very major role in circulating water in this, in this southern portion of the bay. All right, so the first case I want to discuss, this is case A3, which is the natural circulation patterns. I want to talk about this one first, just because this kind of serves as a baseline that we can use to compare our other cases to, right? Because this is what Fort DeSoto was like before all of those changes happened. And basically what we found with this case is that the flow is very homogeneous across the entire bay, right? You don't see areas where you have extremely fast or extremely low flow. It's overall just kind of moderate, right? So what this means is that you don't get areas where water begins to stagnate, which of course is what ends up leading to those water quality issues. And that is something that we do see in some of our other modeling runs that we ran. But with these, wider tidal conduits down here and then up here as well, the water really gets into the bay very easily during the flood tide, and then it gets back out to the Gulf very easily during the ebb tide. So let's compare that case, right, the natural conditions with the existing circulation. And immediately looking at this difference map, a few things kind of stand out. So you can see that the velocity has increased quite drastically in those dredge channels. And the reason for that is just because those dredge channels are acting as, tidal conduits, right? They're concentrating the flow of water that's coming in from Bunce's Pass, and they're helping it get down to the southern portion of the bay. And you can actually see the effects of these dredge channels all the way down at this extreme southern portion of the bay, including at those two bridge openings. Okay, so one last thing to point out on the existing circulation patterns. So you can see that overall, we have this sort of counterclockwise flow trajectory, right? During the flood tide, this water kind of goes in a counterclockwise direction. During the ebb tide, it reverses direction and follows the same path back out. There is one thing I want to point out. So at Bridge 1 and Bridge 2, the flow is going in the same direction, right? Take note of that, because later on, we will actually see something a little bit different in one of our other cases. Okay, so this is the first hypothetical case I want to discuss. This one's actually quite interesting. So in this case, we decided to reopen this historic, tidal conduit right up here near the Fort DeSoto campground. And this is kind of located right in the middle of the bay. But of course, this opening here remains closed to this day, right? If you go out there today, you will not see this opening. But we thought it would be kind of an interesting thought experiment to open this up to see how that would affect the flow patterns. And when we did this, we actually found that a very large percentage of that flood tidal prism is actually diverted eastward during the flood tide. So this opening is actually a very efficient way for the water to get across the bay. Water is always going to follow the path of least resistance. And in this case, this opening right here is the path of least resistance. Okay, so this slide kind of shows how that diversion affects the overall circulation patterns. So what you can see is this kind of brand new flow trajectory that has sort of emerged from opening that tidal conduit. So those tidal currents coming in from Bunce's Pass, instead of continuing southward, they're diverted eastward. They kind of meet with these southward flowing currents coming in this direction, and then they all exit the bay together at Bridge 2. So you see a very, very significant increase in flow here at Bridge 2, and then an increase in flow kind of all along this trajectory here. However, because a lot of that water is kind of being intercepted here, there's not enough for it to, kind of fill this southwest portion of the bay. So as a result, we actually see a reduction in flow across this entire southwest portion of the bay. So while opening this pass here, it sort of stimulates flow in some areas, it actually restricts flow in other areas. Okay, so in this hypothetical scenario, we actually decided to sort of fill in those two north-south oriented dredge channels. Right, you remember those two dredge channels that kind of lead all the way from Bunce's Pass to the southern portion of the bay? We just filled them in. We filled them in and we kind of looked at how that affected the flow patterns. So as you would expect, you fill in those dredge channels, you get a decrease in flow in the channels, you get an increase in flow in the seagrass beds. That's not all that surprising. What is surprising is what I'm going to show on the next slide here. So this is by far one of our most puzzling results that we have in this entire study. We were completely befuddled by this. So recall from the existing circulation pattern that the flood currents at Bridge 1 and 2 go in the same direction, right? They go west to east during the flood tide and then east to west during the ebb tide. However, when you fill in those two dredge channels, you actually see a reversal in flow at that second bridge, right? There's a reversal in flow, so it's no longer going in the same direction. and not just a moderate reversal. You're seeing a strong full reversal in flow during both the flooding and the ebbing tide. So this video here actually shows it. If you look closely at the bridges, you'll see that they're consistently going in opposite directions. There's a divergence in flow at those two bridges. And this is not something that you see if you go out there today. You'll actually find today that they're flowing in the same direction. So I'm not going to get into why this is right now. I'll talk about that in a moment. All right, moving on to our summary section. So one of the major questions that we set out to answer here was how those two bridge openings kind of contribute to circulation. So here are a few takeaways. So based off of the tidal prism analysis, we found that about 25% of the flood tidal prism passes through those two bridge openings during tidal cycle. And what that tells us is that those bridges play a very significant role in facilitating circulation. We also found, and this is something else that was kind of interesting, we found that the discharge through one bridge decreases when the other bridge is artificially closed. So that tells us that there's sort of a hydrologic link between those two bridges. There's a current pattern connecting the two of them. All right, one last thing to note on the bridges. So another thing the model allows us to do is visualize the area of influence for the bridge openings. And that's what's kind of shown in this image here on the left. So this yellow coloration down here is basically showing the area of influence for bridge 1. And when we look at this and we compare it with the area where we had sort of recovery of seagrasses following the construction of that bridge, we actually see that there's an overlap in the area of influence for the bridge and the areas where we saw the most kind of extensive recovery of seagrasses. So this kind of confirms that the bridges were really instrumental in improving the habitat quality and improving the circulation in the Southern Bay, which facilitated this massive recovery of seagrasses. Okay, so this is kind of the summary here, just to tie everything together. So one of the major questions that we set out to answer here is how exactly have the circulation patterns at Fort DeSoto, been affected by all of these engineering activities that have taken place? And this slide here is essentially a conceptual model that summarizes exactly what happened. So in the existing circulation patterns, which you see on the right, you have these two very large north-south oriented dredge channels. They basically concentrate the flow of water coming in from Bunce's Pass, and they help it get down to the southern portion of the bay and through these two bridges. And these bridges actually constrict the flow, so you have extremely fast flow. The fastest flow we found anywhere in our modeling domain was actually at these two bridges. Now, another effect that these dredge channels have is they actually reduce the flow over the seagrass beds. A lot of that water is kind of being diverted into those dredge channels. There's not enough left for these seagrass beds, so we see a reduction in flow there. Now we compare that with the natural conditions. And in the natural conditions, we see very homogeneous flow right across the whole bay. No areas where you have extreme flows, no really fast or really slow flows. And then something else I want you to kind of pay attention to, and this is what I talked about with that divergence in flow at that second bridge. Another kind of key difference between these two cases is that with this case, we actually see this convergence zone, right? This convergence zone between these two islands here, where all of these different flows are kind of leading to, and then they all just stop and they kind of create this gyre here. So when those dredge channels were dug, our theory here is that, or our hypothesis here is that when those dredge channels were dug, there was so much water coming down in this portion of the bay here because it's such an efficient tidal conduit that you actually had a pressure gradient develop. So you had higher pressure on this side of the bridge, lower pressure on this side, and that actually kind of impinged on those incoming tidal currents coming in from Tampa Bay, and it actually caused a reversal in flow at that second bridge. And that completely eliminated this convergence zone. So this convergence zone is no longer here. This is something that only existed back in the 1940s before any of those changes were done onto this bay here. So pretty interesting finding there. Okay, so with that, I'd like to kind of open up the floor for questions. I've included this slide here, kind of just a list of topics that were addressed in my discussion section in my thesis. I'm not going to go into these now, but I'm kind of going to just leave them sitting here for my Q&A session with the hopes that it might stimulate some conversation, maybe get people thinking about new directions for future research in this field. But at this point, I'm done. Thank you for your time, and I welcome any questions that you have.
Okay, so thanks. This is Ping. Thanks, Gray. And at this point, I see we have some participants, and we open up the floor for question from the audience other than the committee member. Any questions from our audience? Okay, any questions from our audience?
No question. I just wanted to say good job on this, Gray. Cheers.
Thanks, Nick. Appreciate it, man.
Okay, last call. Questions from the audience? Okay, well, I guess at this point we go to the committee for questions. And Mark and Kai, since I have been working with the whole project throughout, and maybe you guys can start. I do have some questions later on.
Do you want to go first, Kai? Or do you want me to go?
I have a brand new computer set up today, and so I'm doing things like searching around for what screen holds my mute button. Sorry for the delay.
We can hear you now.
But yeah, good job, right? That great talk.
Thank you.
So it looks like you were part of a bigger project. Could you go back to that first slide where
Absolutely.
As a matter of fact, he did that up. I actually don't know the other 5 parts. I don't know where he did that. At one point, we're going to communicate with each other.
So this hydrodynamic model then, I guess, is informing the other groups, or what's this, or is this taking place at the very after all this other stuff has happened?
Yeah, it's kind of a weird timing, in actuality, because a lot of this work a lot of these other subtasks have actually been completed already. So if you go out there, you'll actually see a lot of that, those mangroves that have been planted, and they're pretty large now. So they've been growing there for a while. So that's already been completed at this point. It's kind of just, maintenance. The seagrass monitoring, I believe, has also been completed. And the water quality monitoring, that's been done too. So I actually was able to get my hands on some of that water quality data. And I reached out to some people at Pinellas County to get that. So I have had some communication with the other groups that are involved in this study. But the Tampa Bay Estuary Program Technical Advisory Committee is really like the platform where I'm planning to share all of our results here, probably a much more detailed presentation. So that's what we're going to be hopefully doing soon. I think there's a TAC meeting coming up soon, and all of the different people involved in this project will be there. So we'll kind of share our results at that point.
So was your focus more to assess what changes the bridges had made?
Yep.
And then you tacked on the scenarios modeling, or was your focus to evaluate different things they might implement in the future?
Not explicitly. That's something that we kind of just did on our own. Kind of the overall goal for us, on paper at least, was really just to quantify the influence of those 2 bridges, to show how they're affecting connectivity, how they're affecting circulation, specifically in that southern region of the bay. So our focus was the bridges. The dredge channels was kind of a secondary thing that we looked at. recreating the natural conditions. That was also sort of a secondary thing that we looked at. So we just kind of expanded on the tasks that we were given.
So when you went out there, you took measurements on the bathymetry and the tidal levels in which locations?
Let me show you. I actually have more slides down here that I moved. So this kind of shows basically where all those measurements took place. So these blue dots here show where we put our velocity meters, and we used acoustic Doppler velocimeters for the velocity measurements. And we put them at the bridge openings, basically because that was kind of the area that we were looking for some sort of a response. The tide level gauges, we actually stuck way out here, kind of closer to the boundary of our modeling domain. When you stick them closer to the boundary of your modeling domain, you get like a more efficient tidal forcing. So that's why we stuck them way out here. So that's the location. So 1 tide gauge, 2 and 3, and then those 2 velocity meters. The bathymetry data, you also asked about that. Let's see if I can find that slide. Yeah, so the bathymetry data, we actually collected a lot of this for a different project. So this was done before I came to USF. This bathymetry data was collected before I came to USF. This is the raw data. This was collected using a boat-mounted single beam echo sounder. And then what you're looking at on the right is the digital elevation model that was created from that raw data. So this kind of serves as the physical domain, for our modeling or our model system to run. We did kind of fill in some gaps. So I showed me standing there with the RTK. So we had to fill in some gaps specifically. I'm not sure if it's even shown on this map. Kind of this area over here is where we needed to fill in some gaps. So I went out there with an RTK and we just collected points. We just walked around and collected points to fill in areas that were missing.
Can you show me on that slide that I'm looking at right there, where you took the tidal level measurement in the southeast corner?
Yeah, so southeast corner, we stuck one of our tide gauges out here, like there's actually a dredge hole here. Which I have another slide on if you want to see, but there's a dredge hole here and we kind of stuck our tide gauge in this area. So there's a road that leads down. We were actually here yesterday with the students and we kind of got out here, I think using our Zodiac boat, and put our tide gauge out there.
And how about in the other southeast corner?
Yeah.
Oh,
That's southwest.
oh my gosh, that's southwest. I'm sorry.
Yeah.
Yeah, I was mixed up. Okay. Yeah, that one we put right here. So I remember you could see it from standing on this bridge here. So it was about right there in that location.
Okay, that makes more sense. In the other figure, it almost looked like it was on land, and I yeah, what was going, but all right.
Yeah.
Okay, so you had 3 tidal level things. You had really complete bathymetry, and then when you did, I think we discussed this before, but I'm not sure what you did with it. When you did your scenarios modeling, including looking back at the historical imagery, did you try to do any modifications with the bathymetry other than just sort of evening out the dredging channels?
Yeah, let me see. I think I also have a slide on that. Yes. So basically what we did is we went in and kind of painstakingly drew this new landmass boundary. After we orthorectified this, we painstakingly drew that line. I followed the shoreline here for all of these features, the mangrove islands and then Mullet Key down here. For the bathymetry, what we did is you can click anywhere on your model and you can get an elevation instantly. So we went right next to those channels and we clicked around for a while and we, jotted down some elevation measurements, and then we kind of took an average of them and said, okay, if these dredge channels weren't here, the elevation of this area would be approximately however many meters. And then we kind of just digitized those dredge channels and then reassigned that depth value based off of that average.
Based off of today's average in nearby locations?
Right. So there could be some room for error there, right? Because we don't actually have the pre-development bathymetry. We're recreating it. So there's definitely some room for error since, this is a highly dynamic environment. So the depth that we have for these channels in this image here doesn't necessarily represent what we have in 1943. But for our intents and purposes, it does kind of help to replicate the natural flow regime.
Okay, so then you plugged these pieces of information into your model and then decided whether your model was telling you what you wanted it to tell you based on two flow measurements, one taken at each bridge.
Exactly. Yep. So you can see this is the calibration results for bridge 1. So the blue line is just showing the modeled values. Red line is showing the measured values. And they match each other pretty well here. So we actually did 25 different calibration runs, and this was a little bit too much detail for me to include in the presentation, but for the first one, we just applied a uniform friction coefficient to that entire modeling domain and played around until we got a fairly accurate result, but we weren't totally satisfied with it. So then we broke it up, right? We broke it up into the channels and the seagrass beds. And then we did that entire process over. And eventually we landed on, I believe it was this one, so 0.03 and then 0.055. That gave us that Wilmot scale of 0.97.
And what's the last thing, just while we're looking at it, the wind direction, wind gauge?
Oh yeah, so that one didn't really give us any compelling results. We simulated wind both artificially and then using a wind gauge. But in a place like Fort DeSoto, it's not a very large bay, so there's not a lot of fetch. So the wind doesn't play a very significant role. So this ended up kind of not being used really for our discussion very much.
If I inject here, Kai, my idea, basically our modeling domain is too small to consider the meteorological conditions. That was part of the project, part of the task. So that part we had to adopt a different approach. I put up a very strong wind that the flow did not really respond. That's because the domain is too small. In order to account for wind and stuff, I have to include almost all Tampa Bay and part of Gulf of Mexico. Then we won't be able to resolve the bridge if we do that.
Right. We call it a fetch limited system because there's not enough surface area for the wind to really make a meaningful difference.
Okay, so then in the end, you're applying that 0.03 to the land areas where you have channels and the 0.05 or 55 to the areas where you think there's seagrass. And then and you got those based on two measurements, which happen to be at the bridges themselves.
Yes, that's correct.
Was there anything you did else? Did you double check that anywhere else? It seems like those are really, interesting, unusual locations, but then you're using those two validation points to say something about a much broader, more complicated area.
We did, yeah. So we did take some velocity measurements in some other places. So there's kind of two different processes here. There's calibration, which we used, I believe it was the first, I want to say 6 weeks of data to do the calibration, and then verification, which I think
10 days, great. 10
Oh,
days.
I'm sorry, days. I meant to say days. I said weeks. And then the second 5 days was used for the actual verification. So we did take some velocity measurements in other regions of the bay. I personally wasn't actually involved in that aspect of this though. So I can't really speak to it in a whole lot of detail.
If I add a little bit, and it's Kai, the reason this was used because you have stronger flow. We try to take measurement elsewhere. The flow is quite small. So that part of the modeling is called a verification. And of course, the best way to verify is to model this and to check another location. But all the other locations flow are very weak. So we adopt a different approach. So we modeled for 10 days, then we modeled for another 5 days to verify the model still behaves. So we kind of verified through a temporal domain instead of a spatial domain.
What about using the stage data as part of calibration and validation? I mean,
The
you've got three tide gauges, right?
Oh, so the model doesn't really output tide data so much.
It
It
does.
outputs,
The water level, sorry to interrupt you, Gray. You weren't involved in this in too much technical detail because the model was driven by measured tide. So the tide is matched perfectly. And that's because I'm using it to drive the model. It's a small area. So I use the measured tide to drive. So if I compare, for example, the tide at stage 1, stage 2 to then compare with at stage 3, it will match perfectly. Because
So wait. So you're driving the model internally from those 3 points. Is that what you're saying? You're not driving it from boundary conditions?
yeah, it is. The measurement was kind of at the boundary condition. What I'm saying is like I have a measurement at one boundary. Let's look at boundary 1 and 2, then compare with the third tide station at the boundary. They would match perfectly. Simple.
So I'm just still trying to understand that. So those 3 points, one's up by Bunce's Pass, one's in the southeast, one's in the southwest. Those are internal calibration and validation, or they're the measurements you use to generate your boundary conditions?
Okay. Sorry, I didn't want to. So if you look at this 1, 3 is what used to drive, right? They are at the boundary. Number
Okay.
kind of in the interior. I know what you mean, I think, Mark. So if I compare the water level that is calculated with the number 2, for example, number 2 wasn't used, it will match perfectly, simply because I'm using the measured tide to drive it.
Because you've got so many controls and it's such a small.
Yeah. So I have it so tightly controlled. So that perfect match can be misleading. For example, if I use, predicted tide or constituents, or if I'm far away and then the water level is something, because I'm such a small tide controlled area if I want to give 100% match, that would give me almost 100% match.
Yeah.
And before you were saying that you measured the velocities in other locations, but they were too small to use to validate the model. Is that correct?
yeah,
Did
pretty
I
much.
understand that?
Sorry, I didn't mean to interrupt, Ping. I wasn't personally involved in that, so he can speak to it in greater detail.
Yeah, we did do some, Kyle, we did do some measurement, like just to the east of number 1.
Just to the
We have a little handheld current meter. We try to do some measurement. The flow is quite weak. The flow is quite weak, and usually 5 centimeter plus and minus. And then again, because they're quite weak, if I match them, they still would match okay. And but they're, then if you take percentage wise, if you have 5 centimeter, if you're off by 1 centimeter, you're 20%. So there are different ways of looking at this. And also when the flow is so small, and then you have to wonder the uncertainty associated with the meter itself, right? So the meter has the arrows. If I measure around 5 centimeter per second, and the current meter would give me 1 to 2 centimeter per second arrow, and then the measured data come with a quite large uncertainty.
Did you guys consider doing them in the dredge channels? Because that became sort of important in Gray's scenarios.
Yeah, it's kind of tricky to do that. It's a pretty deep area. Some of those dredge channels are deep. That dredge hole is actually 4 meters deep. We had some students out there.
Well, yeah. Okay, Kai, good question. By the time, that's for me, sorry to keep jumping in Gray before the project. By the time I realized that, it was kind of too late. See, by the time I realized that the model was calibrated and verified, we're deep into these scenarios. So yeah, it would be a much better idea if we actually go to the dredge channel and drop the current meter over there for spatial verification.
I just want to add, yeah,
Yeah,
that.
you kind of caught me there. Yeah, because I didn't know. Honestly, I didn't know. I know the channel would have a higher velocity, but but I didn't know they were this significant. So that would be a better place to do a verification measurement with the velocity. But by the time I realized that it was we're kind of deep into the other phase of the model. Okay, good. I'll give it back to you, Gray. This is a little detail when we're doing the modeling. So
Well, although I mean, it's the basis of everything he's doing is how was it calibrated and how was it validated? So
Yeah, the dredge channels are really something that kind of grew organically out of this. You know, it wasn't our primary directive at first, but then once we started actually running the model, we saw how much they were contributing to that flow, especially in the southern portion of the bay. So, you know, in retrospect, it probably would have been good to incorporate that into the calibration. But, you know, at that point, it was sort of, we passed the point of no return.
it seems like it's because you see that sort of thing in so many different locations, you know, dredge channels here and there, that it would be a neat addition when you go to, I don't know, do a next thing or something, is to be able to show somebody that no, this modeling technique really truly works even for areas that are artificially dredged.
Yeah.
Let me jump in.
Mhm.
So since we're talking about calibration, can you go to your the slide that had the Mannings in and all the scenarios you ran during calibration?
Sure.
So phase 2, you decided channel should be 0.03 and seagrass should be 0.055, right?
Right. Yes.
Okay. How do those compare to published numbers?
Okay, so we did look at this actually. I think it was a paper by Fonseca and maybe also Susan Bell looked at this too, right, Ping? And I think it was that, but we actually found that ours were lower. We found that our I believe our friction values were lower than what we found in the literature. But we stuck with them anyways because it was giving us really, really accurate results at those 2 bridge openings. And that's kind of surprising too, because it's the Lassia out there, right? Which has a really, really high frictional characteristic.
I actually thought they were high. So
you thought they were high, okay.
Well, the channel one looks pretty good, but the seagrass
the channel one is almost default value.
Yeah, that's right. It's exactly, but yeah, it's right in the middle of the range. But that seagrass one is high. I mean, it's not like, you know, nobody ever heard of that high. It's just on the high end. In what I just go to Chow, you know, the old 1959 table and stuff. I don't, you know, and if you go to Chow and I've got it pulled up right here. Let's see, where did I find one that looked like it? Oh no, I can't find it. Here's earthen, winding, sluggish, dense weeds or aquatic plants. 0.04 would be on the high end, but that's a little deep water. So yeah, I couldn't find anything that was exact, but you know, you can get upwards towards 0.055. Anyway, I just wondered if you knew that, and then, but you're going where I thought you'd go with it, right? What if let's go ahead and say I'm right, it's high, and you're going to say what?
I'm going to say that it's high because of the species that we have out there and because of the depth. It's really shallow. You know, the estuary, the amount of friction you have is a function of the depth. So if it's shallower, you're going to have a little bit higher friction. If you have Thalassia over, you know, something like Haliduli or another seagrass species, you're also going to have higher friction. So those 2 factors together would probably drive that number up a little bit higher.
Yeah, I missed, and if you probably said it in your thesis, but I missed where you said the thing about Thalassia was sort of on the high end of all those factors. So when you gave the presentation, I mean, I'd already done this and thought like, 0.055, man, that's a big number. Not obnoxiously big, but I was just sort of puzzling over it. And when you showed that slide, I thought, oh, maybe that's it. Plus, you're right, it's shallow.
It's shallow. We actually saw a phase lag too at some of our tide gauges, sort of like a tidal asymmetry when that water is going back out because it's so shallow.
Right.
You know, so
Yeah, you did have that graph. The friction is a very small function of depth.
right. Yeah, that one was in my intro.
Oh, yeah, I remember that. Yeah.
Yeah, this one here talking about basically the dredge
Really
channels.
small function.
Yeah.
Right.
So, what about, let me move on to something else. So, this is Thalassia.
Mostly, yeah. So I was able to get my hands on some data from Pinellas County, and I checked various areas because they did some sampling. A lot of it is Thalassia. There's some shoalgrass as well, and some Syringodium, I think. But it's a lot of Thalassia, basically.
What are the measured temperatures in there?
Oh boy, I would have to check the data. I think it's around like 26 degrees Celsius on average, but I can't rattle that off from memory, unfortunately.
But does it have high excursions? Like, does it rank? Because 26 is within Thalassia's normal range. I think 30 is the upper end. But are there temperature excursions above 30? I mean, I'm trying to get back to the motivation. There, you know, you talked about being interested in temperature. So,
Absolutely.
Okay.
Yeah,
So-
that's something.
I looked through your site description. I was floored that there was a recorded temperature like of 103 degrees or something. I was like, holy cow, it's like a jacuzzi before they put the bridges in there.
Yeah,
Oh,
I think, yeah, I found that in my lit review. I think that was that figure I got from SwiftMud, I believe. But yeah, in that southern region, when we went out to put those tide gauges in, our feet were like burning in the water. It was so hot in some of those areas. You know, I think that was in the middle, like late summer. But it gets incredibly hot there. And of course, you know, there's an inverse relationship between temperature and dissolved oxygen. So the hotter it gets, the less BO there's going to be. There's just not going to be as much of it saturated in the water. So that's really, really bad for the seagrasses. That's basically what happened. That's what led to those die-offs in the southern portion of the bay.
Okay. What about the salinities?
We didn't actually, so I have this YSI probe on my desk back here, but we just rented this last week. We didn't actually use it for our research. So that's not something that we factored in, and that's not something that we ran in our model either.
Okay.
Yeah, so I can't speak to that, unfortunately.
That's fine. So, so why not? So the assumption you made was you can solve this with circulation, which is probably a good assumption. But why not a thermal model or a particle tracking module? Because CMS has got a particle tracking module. Why not apply one of those? Or if
Yeah, it's a little tricky at Fort DeSoto. There's a lot of different trajectories, I guess you could say. So we thought about doing residence time as one of our calculations, but it's complicated in a place like this. There's no straight path for something to leave the bay. So depending on where you drop a particle, you're going to have a completely different residence time, you know, than another area. So it's kind of difficult to make that calculation for a bay like this. It's not straightforward, basically. So we didn't end up using the particle tracking. That was something I was interested in doing, though. We were out there on a boat. I think we were doing some surveys for something completely unrelated, but I was just watching this seagrass getting exported out through Bunce's Pass during the ebb tide. Loads of it, just an incredible amount of the seagrass. And it's crazy just to see that much material being exported from the bay. And that just kind of shows the strength of those tidal currents. So that would have been something very interesting to look at, but unfortunately it was beyond our scope.
seems like you could have put, say, I don't know, just at time 0, you put 100 particles in every cell, and then just get the probability density function to describe how long it takes for particles to leave the domain. I don't know.
That could have been a really interesting part with on your southern bay with bridges 1 and 2, just with the possibility that the water's just sloshing back and forth and these velocities.
Yeah.
How
Another
about
thing,
actually going?
Yeah, if I mean before Green, that's kind of on the to-do list. So we have 5 tasks, right? So we have 5 tasks that we haven't really communicated too much with the other tasks. The way I see this is basically our result would be used by all the other people that measure temperatures and then
Oh, okay. All right.
to kind of link their data. And if we start a particle tracking, we kind of open up a big can of worm, so I haven't, for example, where should I drop it and where should we drop it? And I kind of have to have a goal, like why do I drop that? So far, I figured that would be the input from the other part of the project and go, hey, can we look at this, then.
Yeah, I would think each cell, you just drop a bunch in each cell at time 0 and that's it. Just ask how long it takes for a particle to get from any one of because you get a PDF from any one of the cells then to exit. But the problem you'll run into, by the way, if you do that, Ping, we had this, well, you probably remember this from Hunter.
Yeah.
And I'll ask it as a question, Gray, since this is a defense. So what happens to a particle that leaves the domain by 1 centimeter, 1 cell? Can it ever come back?
Absolutely. Yeah, of course it can come back.
Well, it can, but in the model, can it?
No, once it's out, it's out. Yeah.
Right. Yeah. That was Hunter's problem, was that we had these huge tidal effects, but as soon as it went 1 cell beyond the boundary, it ceased to exist in the world. And we would have these big inflowing tides that would push particles out upstream in Shark River. Well, they're coming back downstream. But once they left the domain, they ceased to exist, and so we couldn't get the true particle residence time. He kept having to expand up the domain until he broke his computer, like it just couldn't process. So then we were looking for parallel processing time, and then we were like, oh well, fuck this. This is just it was a really good idea.
That's what I mean. Like you kind of have to be almost like a sneaky. Like, okay, I'm gonna look at between time 1 and time 2, but not time 3. At this location, if you drop, and then that ball can roll and get really big.
Yeah. No, it just became computation, and you'll have the same problem here because the domain is so small. You'll have particles that'll leave that would, in reality, come right back, but they'll act like they disappeared for all eternity, and they didn't. So.
Yeah, and I did talk a little bit about the residence time in my thesis discussion. We didn't calculate it, but with the velocity data, you can kind of make inferences about the residence time. If you have greater velocity, then it's kind of, you don't have to really go out on a limb to think you would have a reduction in residence time. If you're having faster flows, then that water is going to get into the bay quicker and it's going to get out quicker. So we were kind of satisfied stopping there with just having the velocity. We could make all of the conclusions that we needed to with that. But it is something that we wanted to look at.
Our case is also similar to Hunter's. Our case is kind of difficult because you have, if you have land boundaries all around with an inlet, it's easier, right? So, but if you have inlet and then a bunch of water boundaries around it, and then that really gets into, because the water coming from boundaries, we have just one boundary, then surrounded by land, that make it easier to track, right?
Yeah.
So 2 boundaries. Then I think Hunter has all water boundaries around his domain. That's really hard because
So can you go to your last, or near the end of your talk, you had 2 figures side by side, cartoons, that one right there.
Yeah.
Yeah. So there's a flow convergence of the 2 bridges, right, under the natural condition.
Yes.
Which is what you got when you got rid of the dredge channel, right?
Yeah, really, really cool finding. But yeah, once we
Right,
not both the dredge channels, just this one.
That's that one, right?
Just that one. Yeah, that's the
Yeah.
only one that made a difference. Filling in this one didn't really have an effect on flow here, but filling in this one caused that reversal.
Okay. So is that how you figured out the natural circulation? Like, is that where that left hand, like, how do you get natural circulation?
Well, we ran a model run
Okay. So
we
you
ran a
basically
model.
got rid of the dredge channel in your model and ran that.
Oh yeah. So there was a number of cases where we got rid of those dredge channels.
Okay.
Yeah, for sure. So if I go back to the list of all of our cases, I can point out the ones where those dredge channels were filled. Yeah, so of course the pre-development, they were filled for that. Hypothetical case 4, we also filled them in. And then there was another one we kind of called like max restoration, right? Where we kind of just simulated every single restoration activity that we could conceive of. So we opened up this pass here, and then we filled in the dredge channels, basically to simulate the natural conditions. And I believe that was, yeah, that was hypothetical case 5. So it was those 3 cases where we filled in the dredge channels.
Okay.
And in each of them, we basically saw that reversal. So that kind of confirmed that causal relationship, between the dredge channels. And I think we did some extra runs as well. We didn't include them in the thesis, where we closed one of these and left the other one open, just to kind of really confirm it. And we did find that it was this dredge channel that caused that reversal.
What do you think that, were you gonna ask a question, Kai?
Go ahead. I have sort of a big question, so go ahead and chase this down.
What do you think the effects on your study were that you did it over sort of a discrete time period? I think it was July through early August or something, like looked like a 5 or 6 week period. And you caught, 2 neap tides, but presumably you didn't hit an episodic event, and you didn't hit the dry season, and I don't know. What do you think does that in some way bias your results? Are you missing something? I'm especially interested in what the effects of episodic events might be.
Yeah, no, we didn't look at that. There could have been
For his thesis.
Right. We did simulate
look at
storms.
that.
We simulated storms. But it's not included in my thesis.
Okay.
And
Yeah. So sorry to interrupt, Mark. That's another part that's not part of the.
Okay.
For example, Irma, right? Irma comes in, the entire bay was drained.
Right.
Most of it was exposed. There was a really weird flow pattern.
yeah,
The flow through the channels was like 2 to 5 times stronger than like this. And that's what those wind was supposed to do, but that was too small. So I basically took the measured Irma, that's really, really negative surge, and ran it. We did that, but we decided that's kind of that too much for his scope. So
Okay.
yeah, we had to draw a line somewhere with all the information we included. Since
Irma, because it's very interesting. Like when Irma comes, right, so quickly, the entire bay was almost dry. There was no flow through the 2 bridges. That's interesting.
Yeah.
The flow through those channels upward to almost 0.8, 0.9 meter per second instead of 0.2, 0.3. It was
Yeah. That water dropped so much that our boat and Mark Horowitz's boat settled down onto the bottom of the bay.
yeah.
And then the boats at Terracia Marina, the water's super deep there. They ended up hanging off the docks and pulling out, and ending up dangling sideways. And when it reflooded, every single boat in Terracia Marina sank.
Oh yeah.
We were looking for a new home right after they got rebuilt, and we showed up. We're like, how come there's no boats? And they're like, oh, well, because they all sank in Irma. We were like, oh, yeah, never
I think
mind.
we'll look elsewhere.
Yeah.
So
That's interesting.
the
That's
water-
actually, and also the part that he didn't touch, and the model does allow wet and drying. So, and Irma case, there's a huge bunch of dry, and it actually behaved reasonable.
Okay. Can CMS, does it care about rain? Like, does rain get applied to it? Like if 24 inches of rain fell?
No, not input. You can have discharge from the boundary. That's like a hunter has, have the river coming in, but rain, no, rain is not.
You would pick it up though with your boundary conditions.
Yeah, you can only pick it up from boundary conditions.
Go ahead, Kai.
Actually, I have one small question first, which is, did any of your predicted flows for your various scenarios put seagrass at risk? Do you wind up increasing flow velocity anywhere? Too much?
Yeah, at the bridges. Yeah, at the bridges, because the flow is so great there that it doesn't really allow for that seagrass to keep its footing. So I think we saw velocity there that was like, I want to say like 0.7 meters per second, maybe 0.6 or 0.7.
0.6, yeah.
0.6, right. And that's
On a
what
normal day.
on a normal day, right. So, during a storm event, it's going to be even greater than that, of course. And that's just too much for a lot of these seagrasses. It's just too much flow. There's a slide I wanted to show, but I wasn't able to, about the boundary the boundary layer for seagrasses. So with rapid current, you get a thinner boundary layer, and normally that's good, right? It allows for more rapid uptake of nutrients. But of course, there's always a threshold. There's always too much. So if that boundary layer is just stripped away because the flow is so fast, then the nutrients aren't going to be able to get into the leaf where they belong. Plus, there's a physical limit to the root system, and it's going to just give out over time. So those two things near the bridges, there wasn't a lot of seagrass there, but in the areas around the bridges, there was a ton of it because it was very well circulated in that area. But since there's such a narrow profile and narrow cross section at those bridges, that 0.6 meters per second was a little bit too much.
And what velocity can Thalassia withstand in terms of rooting?
I don't know the exact figure off the top of my head. I believe that's in my thesis. I want to say it's around 0.3 or 0.4 meters per second.
Well, Susan Bell and one of her paper that got out citation. Well, again, sorry to interrupt. This is interesting. They got the 0.25 as some sort of a threshold. About 0.25, it become an unfavorable condition. But okay, I hate to be not polite. I do a lot of flow measurement. I'm not so sure. I'm not so sure their measurement, because 0.25 is pretty strong.
Yeah. I've seen lower than that, but for different species. I honestly didn't know what Thalassia was.
Move the bed, and I'm not 100% sure. They did that in North Carolina. But 0.25 is a pretty strong flow.
Of course, Thalassia is a rhizomatous species, so it reproduces vegetatively. So it does have this like underground network of roots, and it can stay there with a good amount of flow. But there is too much. Too much does exist. There is a limit, and what was happening at those bridges was definitely reaching the limit. Also, when we opened that campground pass, we saw really strong flows there. So if they were to ever reopen that, we would see the same thing. We would see flows that are too strong for seagrasses.
So you're going to be a consultant, right?
Yeah, I actually just started.
Already started.
Yeah, I've been working at JMT Engineering now for about a month.
So if you, just forget about your thesis for a second here. Just no emotional involvement in it. If you were hired to evaluate one of your scenarios, let's say opening campground pass, and you had to propose what studies you should do to make sure this wouldn't be a bad thing, like what more information? Let's say you had access to your own thesis, but what more information do you think you'd need before you could evaluate whether?
Yeah, well, I mean, we would need to just evaluate whether or not it's a necessary undertaking. I would want to see a really, really extensive water quality, seagrass, habitat monitoring survey done in the vicinity of that pass to see if there's any impairments at all that would justify a project of that scale. So NOAA actually produced a list of indicators that they use to kind of identify these hotspots, these areas along causeways where you see really, really severe restriction. And I would basically go through that list, and I would just measure all of those parameters, water quality, seagrass health, temperature, so on and so forth, and see if we're getting those flags, we're getting those hits in that area. And then we would kind of do a cost benefit analysis to see if it would be worth it to reopen it. And then the modeling is also important. You know, the modeling told us in this case that reopening that pass may not be such a good idea, right? Because sure, it's gonna really, really facilitate flow up there in the northern portion of the bay, but it's gonna restrict flow in the southwest portion of the bay. So we would want to take that into consideration as well.
Okay, that's actually one of my questions, Greg. Can you expand on that a little bit in terms of the overall flow patterns in the bay?
Sure. You mean like, so basically from a ecological restoration?
No, from
sort of-
the flow pattern, right? So if you look at the bay, there's north and south flow, and then the bridge and the campground pass is the east and west flow. Kind of discuss that from the flow direction point of view.
Yeah, I mean, basically that causeway, what it did was it obstructed that west to east flow pattern. That was the primary effect that it had.
Yeah, but by obstruct the east and west flow pattern, what would happen?
You would cut off the connectivity. You would basically divide the entire estuary system into 3 separate estuaries, right? There's now these.
But the same amount of water still exchanges. It would force the north and south flow a little bit stronger, right? We see that in the results. Flow cannot go east and west, and then they may be more guided towards north and south.
Well, what happens when you don't have that east-west flow is the water is just going to fill in those areas in the southern portion of the bay. It's not really going to have anywhere to go as it approaches the slack tide. And during there's probably a period of a couple hours where it really just sits there because it's not flowing through those openings. It just sits there, and that's where you get the temperature loading. That's where you get the water quality issues. And then when it finally does start flowing out, it drains slowly, right? It's going to drain very, very slowly because there's no conduits for it to go through. It just kind of has to follow the same restricted path back out. But when you have those large tidal openings, sorry, I'm looking at my map of Fort DeSoto I have over my desk, but I don't have it on the screen here. When you have those larger tidal openings, there's a greater amount of efficiency in the way that water gets out of the bay. And also
but however, the two bridges are located at the bottom of the bay. The campground pass is located in the middle of the bay. So certainly it's beneficial to allow east-west circulation at the bottom of the bay. However, if we try to stimulate this east-west circulation in the middle of the bay, would that be, there can be plus and minuses, right?
Yeah, I mean, the plus there would be that you're creating a more efficient route for the water to get to that central compartment. It's much more efficient. It's closer to Bunce's Pass. The water goes right across. But that entire southwest region of the bay, which I shown earlier, is going to be starved of water, right? Because all that water, where's that new flow trajectory? All that water is no longer going there. Instead, it's flowing down here, and that's why you see such an increase in velocity of this bridge, because it's just getting pumped into this new gyre, and it's just going straight out. So you see these large reductions.
Yeah. So in that aspect, if I argue, by doing that, you improved the circulation in the part of the bay that doesn't really need to be improved.
Right.
The part that really suffering is getting even worse. Right.
Exactly. Yeah. And this becomes a philosophical question, because when you look at ecological restoration, there's several different schools of thought, but a lot of people are in the team where they think, we should recreate natural conditions. That should be the goal. We should take whatever system we have, we should find what it was like when it was natural, and we should try to recreate that to the best of our abilities. In this case, reopening that pass would simulate the natural conditions for sure. Absolutely it would, because that pass was there in 1943. But that's not necessarily going to solve our problems, because that could actually create more issues in the area of the bay where we see the worst water quality issues. So then we kind of have to ask ourselves, okay, maybe we should create like a new target ecosystem. We should create one that is sort of a happy medium between the different, the natural and the pre-development, or sorry, the existing and the pre-development conditions.
Okay, that's my second question. You kind of answered it.
Okay.
That's my two questions.
So currently the worst water quality is still in the southwest corner, right? Or
Yeah,
that's where the flow, you'd like to see more flow if you could.
right. It's funny, the students are upstairs right now analyzing that data. So once they have those results, I'll be able to tell you. But let me see if I can find a photo. There's an area that is just atrocious.
Area with the hole.
The hole, yeah. So the county, sorry, not the county, is Tampa Bay Estuary Program. They made a dredge hole synthesis report back in 2018, and they identified all these different dredge holes. Where is the photo? Oh man, I think I deleted it. Anyways, they identified all these different dredge holes in Tampa Bay, and this was on the list. This one right here, it was pretty high up on the list too. So what happens in this dredge hole is you get stratification of the water. This area is already poorly circulated, but when you stick a giant dredge hole here, it's very difficult for water to kind of flush through here in a way that's conducive to good water quality. So you get a stratified water column where in that very bottom layer, you have anoxia. You have benthic communities that are starved of oxygen and they end up dying off. So they consistently found anoxic bottom layers in this dredge channel right here specifically. So this is on the list to refill this dredge channel. So that's something we looked at. Kind of danced around your question there, but I hope that answered it.
Well, no, that was sort of my launching pad. So what I'm trying to do is I'm trying to figure out which of your hypothetical scenarios is most likely to actually catch someone's eye, and maybe someone will get excited about moving forward with it. You know, if you're presenting this to the county or whoever you're presenting it to. So with that one, if somebody really wanted to improve circulation right there in that hole, which of your, was it just filling the hole was your best? I thought that one had a complicated outcome. What's your best scenario for getting rid of that stagnant water in the southwest?
There's no easy solution for that. You can't breach anywhere here to provide better circulation. No one's going to be cutting a new inlet, in Fort DeSoto. So we have to stick with something that's practical and feasible. So the best thing that they can do is get rid of those dredge holes, and that's really the plan right now. I mean, another alternative would be to widen this bridge out, create a wider conduit. You might get more efficient flushing of water through here, but that's also kind of a project that you have to really ask yourself if it would be worth doing. The value proposition on that may not be enough to actually justify such a project. You know, it's impressive that they were able to do this much. So I think that the best option, you know, from a really practical sort of perspective would just be to fill in this dredge channel.
By the way, Kai, this is actually, we had one meeting with Tampa Bay Estuary Program, kind of communicating. This is one of the scenarios they recommended. We have it in grade 10, hypothetical. Filling it would have almost zero influence on the overall circulation. However, it would help with getting rid of those stratification. Another.
Okay, that was going to be, yeah, that's where I was headed. So it doesn't, there was no other change that induced somewhere like to the north of the hole or in the dredge channels or.
Yeah, well, another thing that we haven't really considered in this study and wasn't part of is the wave forcing. The wave can be can help mixing. The water is quite shallow, and the wave can really penetrate to the seagrass, to most of the shallower area. When you have something that deep, and then the potential mixing that can be caused by wave forcing is eliminated. So what's it about the students' data, you know, below 1.5 meters, it really just sits there. Well, everywhere else, when we have a wind event, you know, we have like a winter time when the bay got drained, they can kind of help. You know, they won't get the regular flushing, but they may have event flushing. So at one point, I may look at the potential wind forcing. Yeah, the potential wind forcing that can help mixing the water.
Yeah.
But we know there's no wind, there's no mixing by wave forcing.
I just want to point out how we looked at that dredge channel. This is a different case, but we did this for every single one of our cases. We just kind of compiled all the velocity data for those extraction points, and then we compared them to those existing, right? A2 is the existing one. So picture that this column is actually for that one where we filled in the dredge channel. And we looked at those percentages and they all remained constant. There was no change, except for, I believe, at the extraction point S2. We did see some change there because that's really close to that dredge channel. I think we saw like an 11% increase in flow in that area, but everything else was pretty much constant. So that, you know, finding nothing is actually finding something in some cases. So when we filled that dredge channel in, it didn't really affect the flow pattern. So go ahead and fill it in. You know, that's what we can, that's the information that we can give to the county. We modeled this and it, sorry, go ahead.
Oh, and an extraction point is just like a grid cell that you focus your attention on.
Exactly.
And this is the velocity that the model returned for that grid cell.
Yeah.
Yep.
Yeah,
Exactly.
yeah. From
So-
my point of view, sorry to interrupt, Kai. From my point of view, so the flow map they show is like a snapshot over, let's see, 10-day period. But those locations, I can extract the tide of the flow for the entire 10 days, looking at the temporal variation
Mhm.
as well here.
Yeah, I see why you would want to do this. I guess where I was hoping to head with my, consultant question, anyway, I'm just going to get there because I feel like I'm hogging a lot of time, which is that I would be, that I hope you are a little worried about the fact that somebody could take what you did and make assumptions or just buy it lock, stock, and barrel. But there was no validation in some of these really important extraction points. So if if you were a consultant and you were able to propose an addition to this, I guess I would just hope that you'd go out there and take a look and make sure that the velocities in some of these key points are really doing what your model is predicting that they're doing today, so that you'd have a higher level of confidence for what is predicted to happen given your various scenarios. Because I could see this being really exciting, and the local community getting really excited about it. That would be the one thing that if I were you, I'd kind of like, okay, but before we act, let's just, go out there and take a couple of velocity measurements and make sure that.
Yeah, there's always uncertainty in modeling. It's a prediction and we can never be sure that it's 100% accurate. So we shouldn't blindly trust it. We should never blindly trust it. We should always verify. So I would definitely say if there was going to be some sort of a decision made based off of these results, it's something that we would want to verify first.
That's a really good point, Kai. And so calibration and verification is always open-ended. How do I say this? Open-ended debate. But so if we move forward in your track, it wouldn't be too hard to drop a velocity sensor into those channels to get some measurement to confirm.
Yeah, and I think that would really help quell
Yeah,
any disturbance that a reviewer might feel too, that if all your validation just took place in two bizarre corners of the model, and yet you're saying stuff about very different areas, shallow areas, dredge channels, areas behind barrier islands, that sort of thing.
Yeah. Many times, the modeling scale can be deceiving. We picked, if you look at his number, we picked the most forgiving one. That's why he's getting 0.97. There are other ones that'll be a little bit tricky. So if you look at that scale, the larger number will give a better. So a smaller velocity will.
With the percent differences.
Percentage difference. See. Right. Yeah.
I just have one last question or conversation. What do you think this has taught you about the biggest limitation to this type of approach? Like what do you think is the biggest limitation to sort of coastal estuary modeling? Or I can think of a couple, but I'm just sort of curious what your thoughts are.
So I would say resolution is a problem. So I can actually show a slide to show what I mean. We needed to get really good resolution. Shoot, I don't have that slide either. We used a 2x2 meter grid cell for our bridges, but we couldn't use that across our entire modeling domain, right? Our model would crash if we tried to get resolution that fine. So we had to actually do a telescoping bridge, or telescoping grid at the bridge openings, and then expand that to 8 meters for the remainder of our modeling domain. So if we wanted really great resolution at any point in those other regions of the bay, we wouldn't have it. You know, we would have to redo our model with another telescoping grid. So that resolution is a limitation, I would say. I mean, 2 meters is pretty good, but if you're wanting to get if you want to get down to the minutia, that's definitely going to be a limitation. And another limitation is that there's other things going on here that, you know, what we're looking at is lateral changes. There's also vertical changes, right? There's stratification of the water column. There's density currents. There's differences in salinity based off of how high or low you are. And our model is depth averaged, right? It doesn't actually account for that. So that's another thing, that's another sort of limitation here. You know, looking at those vertical differences is also something extremely useful, extremely interesting, that could help to really strengthen our results, but that's not something we have because that's just a limit. That's just a reality we face when we're using this type of a modeling system.
About geomorphic change.
Yeah, so like sedimentation, you mean, and erosion.
Yeah.
That's something the model can do. You can actually simulate sedimentation, and you can even calculate sedimentation rates using this model. So I wouldn't necessarily consider that a limitation. That's just not something that we did for this study.
Can it simulate erosion too? Like, can it simulate bridge scour?
I believe so. I mean, to my knowledge, yes. I haven't done that personally, but I believe if it's able to do sedimentation, I don't see any reason it can't do the inverse of that, which is erosion.
But
Yeah, it can, but if you try to simulate scour, then this depth average velocity is gonna really hurt. So they have 3D models. However, 3D models so computational intensive, then you can only run in a very small area for a very short period of time. Then the scour doesn't really happen in a short period of time, right? So, and
yeah, Hunter experienced the same thing. You probably remember that. He did his also 2D depth average.
yeah.
Because of computational efficiency. Yeah, it breaks down pretty quickly.
Yeah.
It does.
Okay.
And
Right.
also sedimentation and erosion computation, mostly empirical. And the hydrodynamic part, all these models, they can actually do pretty well. Then the sediment transport, we are happy or lucky if we can get within 200%. And then if we can get it within, we can get the direction right. Then translating to erosion and sedimentation, then it's really hard.
Yeah. Hunter hated even the particle tracking component, and he wrote his own in MATLAB. He thought it was much better.
Yeah, that's interesting. Yeah.
So yeah, it's a little clunky.
Mm-hmm.
That was my last question. I don't have any more.
More questions, Kai?
No, although what is your new job?
I'm an environmental scientist.
The job offers.
Yeah, technically I'm an environmental scientist. That's going to be my job title. I'm working at JMT in Ybor City. It's one of 3 offices that they have in Florida: Johnson, Murmurin, and Thompson. I'm not sure if you're familiar with JMT. There was a girl working here, and she moved to Alabama, so she was handling all of the environmental stuff for this office. and that left a giant hole that they were trying to fill. So they scouted me at a networking event, and they, kind of reached out to me on LinkedIn, and then things went on from there. And I eventually started meeting the supervisors and the managers, and then they just hired me on right out of grad school.
Will you be doing coastal stuff or inland
Yeah.
stuff? Or?
Yeah, I'm going to be doing coastal, going to be doing some wetland work. They had a modeling project at the US Virgin Islands that we were trying to get. And it was a sargassum modeling project where they were trying to figure out why that sargassum is getting onto those beaches and how to stop it and so on and so forth. We didn't get the contract, unfortunately, but there's another project in Martin County, Indian River Lagoon, that we're still trying to get. So that's a coastal project. Hopefully I'll be working on that. I was doing zooplankton surveys the week before last until 2:30 in the morning on the Hillsborough River. So that was fun. You have to do zooplankton. Yeah, you have to do that at night because they're not active during the daytime. And I learned that the hard way.
Oh, well, that sounds really interesting. That you're gonna see a lot of territory, do a lot of stuff. Good for you.
Thanks.
Well, so if we don't have any, I don't know, I guess Gray is the host, and I think the committee need to discuss. Maybe you can just step away and we can have a quick discuss. I don't think you can leave the meeting. If you leave the meeting, I think we're gonna end.
Yeah, that's okay. I'm gonna go ahead and stop the recording. Y'all probably don't want this discussion